Let's take a further look at implementing our digital logic design with NAND gates and NOR gates. In this video, we'll specifically focus on NAND gates, but let's take a further look at the reasoning for that. NAND and NOR are easier to fabricate with transistors than AND and OR gates. We saw that in the first module. There's literally 2 less transistors in a NAND gate than an AND gate, and 2 less in a NOR gate than an OR gate. So NAND and NORs are the basic gates of all the digital logic families. So our conversion between implementation with AND gates and OR gates to NAND gates and NOR gates, it's proceduralized, and that's what we'll look at in this module. Again, in this video specifically for the NAND gate. It is the universal gate. We can implement any gate with a NAND gate. For example, an inverter is just X. If we put X into both inputs of a 2-input NAND gate, at the output we will get X prime. We'll get the inversion of X. And you can prove that to yourself with a truth table, but basically NAND is AND invert. So 1 and 1 is a 1. We invert that, we get a 0. 0 and 0 is 0. We invert that, we get a 1. So we can show that we can use the NAND gate as an inverter. The AND gate, we just need to invert the output of our NAND gate. So what we have at the output here, we have our XY prime, and XY prime prime, then when we invert it again, is equal to XY. So our AND gate, we do need 2 NAND gates to implement it, but that's how we can use a NAND to implement an AND. And further, we can implement an OR gate. So our OR gate is going to be our X or Y. If we work backwards, we can work backwards. This is proof that this is, again, our X prime, Y prime. So X prime and Y prime, prime the whole thing, we get X or Y. Or we can work in reverse. X prime prime is equal to X prime, Y prime, prime, using De Morgan's theorem. So this is our universal gate and how we can implement an inverter, an AND gate, and an OR gate. So basically our NAND, that's the AND invert. No matter how many inputs we have going into the NAND gate, we take the AND of them and then we invert the output. Well, if we use our De Morgan's theorem on that, what it is it's the OR of the inversion. So the AND invert is the equivalent of our invert OR. So we have this equivalent symbol of a OR gate with bubbles at the input, and this is an equivalent symbol to the AND gate. It's mixed notation if we use them both, but we can use this symbol to represent an AND gate because an invert OR is equivalent to an AND invert, and that's shown here with our algebra. So if we wanted to implement our function, F is the sum of AB ORed with CD, we could use our involution theorem and invert it twice. So we take the double prime of our function, and then we distribute one of the primes or one of the inversions, and by using De Morgan's theorem, we get our AB prime. So we get the NAND of AB ANDed with the NAND of CD and invert the whole thing, so we end up with a NAND. So we show that with our algebra, but basically what we're doing is our involution theorem. What that is it's a double bubble. So if I put a bubble here, that's an inversion, I need to put another bubble here. And then I did my double bubble. There's our involution. If I do it here, I need to do it here. So I've done it twice on the line, so I've double bubbled both. That's our algebra, showing it schematically. And we see here, this is our mixed symbol, but it's an alternative symbol for a NAND gate. So now we've made that a NAND gate, and we've made this a NAND gate by adding these bubbles. So we end up with our NAND. If we don't want to use this mixed notation, we can show the schematic with AND invert for our second level gate as well. And all of these are implementing our sum of products. But it's nice and easy to be able to use this involution theorem right on our schematic. Anywhere along a line, if we do a double bubble, that's basically the involution theorem, and we've created equivalency. So our procedure, we simplify the function to sum of products. We draw a NAND and invert for each product term. If we do have a single literal that doesn't go into a product term, then we have to invert that. We can invert it with a NAND gate or show it inverted with an inverter. And then we draw a NAND invert OR for the sum of each of the product terms. So for example, if we were going to implement this function, I'll just do it on the next page so I have a little bit more space. I have AB, that's a product term. So it says I'm supposed to use a NAND for that. And I'll just draw A and B at my input. And then I have A prime C, A prime C for my second product term. And then I have a D prime and an E. So my D prime, I'm going to have to invert that, and I'm just going to show an inverter to invert it, and then as opposed to a NAND gate. And then my E, I need to invert that. And then for the second level, I'm going to have 4 inputs, so I use the invert OR instead of the AND invert. And there I have my my implementation. Now here what we have is E prime, and here what we have is D, so we don't really need this inverter. So when I'm actually implementing this, I'll show it with just I'll show it with just AND invert, but I'll do AB. I'm still going to show my A prime C, and here what we have is just D, right? So we just need D, and we need, I'll just show E prime without show, since I didn't show the A prime inverter, I'm not going to show the E prime inverter. And there is my function just using and invert symbols. So this function was already implemented as sum of products. Notice that without these bubbles, right, without these bubbles here, it's simply the and or. But we do have to be careful, since what we had is D prime, what's going into the second level NAND is D, what we had is E, going into the second level NAND is E prime. All right, let's look at another example. Here we have to simplify. We want to simplify this function and implement it with NAND gates. That means we're going to simplify as sum of products. So first we have to load the function with minterm 1, minterm 2, minterm 3, minterm 4, 5, and 7. Now we're going to simplify in sum of products. Well, we've got this term here in the middle. That term is just going to give us, that's going to give us our x changed. The only thing that didn't change is a y, right? Yeah, no, a z, sorry, z. So we get z ORed with, now we're going to have to circle 2 more terms. So we get c ORed with x, y prime, and ORed with x prime y, x prime y. So now we want to implement it with the NAND gates. So what we have is z. We're going to have to put that through an inverter. So instead of putting it through the inverter, I'm going to use my z prime. But first, you know what I'm going to do? I'm just going to I'm going to show the implementation with and or, right? So we'll do it all in red. And so my AND gate here will have x and y prime. That's the second level one. And then we have our x prime, y, and we'd have the OR of the three of that. We need to OR these 3 terms. But now we need to do the involution, the double bubble. So if we do a bubble here, you do a bubble here, bubble here, bubble here, bubble here. Well, how are we going to do that bubble? I'll put a prime there, or you can show an inverter, but that's going to give us our function implemented. So if we were to draw it with just and invert notation, again, the x and the y prime, that's the same as this term, the x prime and the y. Did I do these right? Yeah, I did. That's the same as that term. And then we have the z, it's the single literal. So instead of z, we're going to do z prime, and that's a bubble. And there's our NAND implementation with just and invert. So we can use this double bubble or involution theorem, excuse me, on any circuit. So this is not a 2-level circuit. This has 1, 2, 3, 4 levels. C has got to travel through 4 gates before it gets to F. But without changing the circuit, we'll just change the implementation to NAND. So I double bubble again. So I'll show the inverter. Got to get a bubble on both sides of the lines. Here, I want to change this to a NAND. So I need to put a bubble here, and that's nice because that's a NOR, so we can do our OR invert. And this, we don't want to change this line, right? Because we have the output of this. This now is an invert OR, so that's a NAND. An AND invert, that's a NAND. Invert OR is a NAND, and an AND invert. So we've just changed this implementation to all NANDs. We didn't change the diagram. We didn't, we still have this and or implementation, but we just changed these AND gates to NAND gates, and we actually just changed the OR gates to NAND gates also. But we did have to add an inverter here for B. When our final implementation shown here, just a little bit nicer with the invert OR notation, so it's a mixed notation, and the AND invert notation, and the key here is this single literal. We had to make sure we inverted that, so I just showed the prime there. So to itemize our procedure, then our procedure convert and or to all NAND, so all AND gates become NAND gates with an AND invert symbol, all OR gates become NAND gates with an invert OR symbol. And then we want to make check all bubbles in the diagram. For every bubble that you have inserted, that if it's not compensated by another bubble, then you have to insert an inverter. Or, sometimes we just show a complemented literal, which is essentially putting in an inverter. Sometimes what you're doing is removing an inverter for the second bubble. All right, let's look at one more example here. So if we want to implement this circuit with NAND gates, with NAND gate circuits, again, I'm just going to draw it as is. So I'll get my AB, A prime BC, right? So there's A, B, A prime, B, C. And now that's going to go into an OR gate. Well, we better draw that a little bit further because we have 2 OR gates and an AND gate. So I'll bring this OR gate out a little bit further. Whoa, there we go. There's my OR gate. And now I have 2 ORs that are ANDed together. So I have this OR and I have this OR. And what I have here is A prime, B prime, A prime, C prime, and these two get ANDed. And then we have 3 inputs to our final OR gate. So here is the implementation as expressed in this Boolean function up here. Now, if we want to convert this to NAND, well, this is easy enough since this is and or. We just have to do a bubble here, a bubble here, a bubble here, a bubble here, bubble, and bubble. So that part, that and or is easy. But for these OR gates, we want to convert those to invert OR. That becomes a NAND. So we have to double bubble that. So this A prime prime just becomes an A. B prime prime just becomes an A. And similarly, they're both primed. So we prime again, and we get an A, and we get a C there. So we do have to be careful. If it's ands feeding ors, we can double bubble right on the same line. If we just have an or at the input here, when we change it to an invert or, we have to invert the literal coming into the input. All right, so this video talked about how we can convert any circuit to a NAND only implementation. In the next video, we'll look at the dual of NANDs, which is NORs.